Welcome to This Explainer. Today, we're taking the invisible force of magnetism and bringing it to life. We are going to explore exactly how moving electric charges shape not just the physical world around us, but our biological world too. It's an incredible topic, so let's just dive right in.
Here is our roadmap for today. First, we'll look at the ancient invisible force, then moving charges and electrons. After that, we'll see how magnetic materials behave, cover the basic rules of magnets, and finally, wrap up with biomagnetism in living things.
Section 1. The Ancient Invisible Force, a History of the Unseen. Let's kick things off with how humanity interacted with this whole phenomenon way before we actually understood the mechanics behind it. It is honestly mind-blowing how massive the gap in time is between observing magnetism and actually understanding it. Around 625 BCE, you have Thales of Miletus investigating these natural magnets called lodestones. By the 1st century, folks in China are literally writing about using these lodestones to attract needles. And then, for centuries, we're navigating the entire globe with compasses. We're talking the 11th century in China, and by 1187 in Europe. But here's the crazy part. We didn't really know how they worked. It took all the way until 1819 for Hans Christian Ørsted to accidentally discover the connection between electricity and magnetism, simply because he noticed a magnetic field popping up around a live wire.
Section 2. Moving charges and electrons, the quantum level causes. To actually understand Ørsted's accidental breakthrough, we have to look much, much closer.
So at its core, magnetism is entirely driven by movement. It's an attractive and repulsive phenomenon produced by a moving electric charge. This is the electromagnetic force, one of the 4 fundamental forces of nature. Magnetism is really just the byproduct of kinetic action. Whether it is a current traveling continuously through a wire or the constant spin of elementary particles like electrons, any moving electric charge inherently generates a magnetic field right perpendicular to it. It's basically the universe's most fundamental animation playing out continuously.
And because all matter has orbiting electrons, literally all matter is magnetic to some degree. If you could see this animated on a quantum level, it's like a tiny, perfectly choreographed dance. Step 1, the positively charged nuclei shift just a tiny bit in the direction of an electric field. Step 2, the negatively charged electrons move the exact opposite way. And finally, step 3, because of this tiny separation, an electric dipole is born. This microscopic kinetic movement is the literal foundation for the force that sticks notes to your fridge and guides massive cargo ships across the ocean. Section 3, how magnetic materials behave. Electrons in motion. So we know all materials have orbiting electrons, but as you're about to see, they behave very differently depending on their internal alignment.
The beautiful chaos of magnetism essentially comes down to 5 main types, and the real game changer here is how unpaired electrons align. In diamagnetism, think water or gold, paired electrons actually cancel each other's spin out, so they weakly repel magnetic fields. But when you introduce unpaired electrons, things get much more dynamic. In paramagnetism, like with lithium, electrons actively align with the field while it's present. Then you have ferromagnetism, found in iron and cobalt. This is what you probably picture when you hear the word magnet. The unpaired electrons align and stay locked in that alignment, creating a permanent magnet. Antiferromagnetism is fascinating because it features an anti-parallel alignment that completely cancels out any net magnetic field. And finally, ferromagnetism, seen in things like natural magnetite, has opposing pairs, but their specific arrangement is unequal, so a strong, active magnetic moment still remains.
Now, what happens if we toss a new variable into the mix, like heat? Well, increasing the temperature cranks up the random thermal motion. Imagine those perfectly aligned electrons we were just talking about suddenly vibrating and bouncing around chaotically. All that energetic motion makes it incredibly hard for the magnetic moments to stay aligned, which physically weakens the magnet. It's a pretty great reminder that magnetism requires a strict level of atomic order, and kinetic heat absolutely loves to destroy order. Section 4. The rules of magnets, dipoles, and planetary fields. Now that we understand the microscopic alignment, let's zoom back out to the macro level and see the unbreakable rules these materials follow. At the macro level, magnets follow some pretty strict rules. Every magnet has 2 poles, and the fundamental law of attraction here is that opposite poles pull toward each other, while like poles actively push away. So north repels north, but north fiercely attracts south. On top of that, these magnets will actively pull in ferromagnetic and ferromagnetic materials, like the iron and magnetite we talked about, and can actually force their electrons to align, effectively turning them into magnets as well.
This brings us to a really cool, unbreakable law of physics. Magnets always exist as dipoles. You might think, logically, that if you take a bar magnet and chop it perfectly down the middle, you'd be left with one piece that is purely north and one piece that is purely south, right? But you don't. Instead, you just end up with two brand new, smaller magnets, and both of them have their own perfectly functioning north and south poles. The dipole is totally fundamental to a magnet's existence.
Now, when we scale this rule up to the size of an entire planet, things get brilliantly counterintuitive. We just established that opposites attract. A compass magnet's north pole physically points toward the Earth's geographic north. But because north is only attracted to south, that actually means our planet's geographic north pole is, technically speaking, a magnetic south pole. Basically, if the Earth was just a giant spinning bar magnet floating in space, the big S for south would be stamped right at the top. Section 5. Biomagnetism and living things. Magnetoception. We've covered ancient history, quantum mechanics, and giant planetary fields. Now let's finally turn the lens inward to living organisms. Because we humans aren't the only ones utilizing this invisible animated force. Enter magnetoception, the biological ability to literally sense a magnetic field. Certain creatures, from bacteria and mollusks to arthropods and birds, can dynamically feel these invisible fields to help orient and propel themselves. It is basically a constantly updating, built-in biological GPS system. But organisms don't just passively sense magnetism, they actively use it in a process known as biomagnetism. Take kittens, for instance. They're a type of mollusk that actually uses moving deposits of magnetite to harden their teeth. But it hits much closer to home too. Our own human eyes contain a shifting protein called cryptochrome, which hints that we might have some latent, underlying degree of magnetic sensing ourselves. Even wilder, humans naturally produce magnetite in our tissues, and researchers believe this might be actively interacting with our immune and nervous system functions. Which leaves us with this final, incredibly provocative thought to chew on. Since our own biological tissues naturally produce magnetite that may be constantly interacting with the Earth's magnetic fields, how much is this invisible, animated force shaping you, physically and mentally, right now? It is wild to think that the exact same kinetic dance of electrons guiding a compass might also be subtly pulling the strings inside your very own body. Thank you so much for joining me for this explainer. I really hope it sparked your curiosity, and I will catch you in the next one.